Gee, I hope you can hear me. आ रही है आप लोगों को?
Yes, sir.
Okay, so we'll continue with our ANSYS Fluent tutorials, and today we'll simulate two supersonic compressible flow cases. So the first one is the flow in a converging diverging nozzle, and the second one will be supersonic flow, a wedge type body. Okay. So so the first case is that we have a convergent diverging nozzle of circular cross section. Circular cross section area varies from inlet to outlet according to a certain relationship. So area is pi r square, and that varies with the axial coordinate. That will be 0.1 plus here, where x is the axial coordinate values. So x ranges from, so inlet sits at x equals minus 0.5, and the throat is at x equals 0. Then outlet is at x equals 0.5. Then we are given certain inlet and outlet boundary conditions. In the inlet, we have, at the inlet, we have stagnation pressure, which is 101325 odd, and stagnation temperature is also given, which is 300 Kelvin. The static pressure at the exit is static pressure 3738.9 Pascal. So we will simulate this flow and look at the results of Mach number, pressure, and temperature distributions. And then we are.
सर अगर आपने स्लाइड शेयर की हुई है तो हमें स्लाइड शो नहीं हो रही
जी
सर अगर आपने स्लाइड शेयर की हुई है तो हमें स्लाइड शो नहीं हो रही
जैन आप रिजॉइन करो
स्क्रीन तो मैंने शेयर की हुई है, सबको नहीं, किसी को नहीं शो हो रही?
सर शो हो रही थी, हो रही थी,
हो रही है शो?
सर मैं चेक कर लेता हूँ सर
आई थिंक हो रही है मेजॉरिटी को, so I'll continue. Okay, so this is the simulation setup, and then you can compare this simulation setup with the analytical results. And analytical results, you can find out various, given the inlet and outlet conditions, you can go to the tables for isentropic flow in a converging diverging nozzle, and at various locations in the axial direction you can find out various quantities like Mach number, pressures, etc. So analytical solution at various values in the axial direction is given in the form of a file, which I have just posted on the Teams as well, which is the name with the name Mach underscore 1d.xy. So what it has got here is, I think the first column is the coordinate values. So it starts from x equals minus 0.5 to throat and then to outlet. And then I think it has, the second column, it has the Mach number values, corresponding Mach number values. Okay. So this is the file or result which this is the analytical result which we will use to compare our simulation results with. Okay, so what is different here from other previous tutorials? We're going for compressible supersonic cases, and what else? Yeah, so we'll start with that. Okay, as ever, you start with ANSYS Fluent, dragging ANSYS Fluent there, convert it to a 2D case. So we will create the geometry in space claim. So I'm starting space claim. So then you go to file options and then convert units to meters. Go back 10 seconds. So I think there's something, okay. So you go to file options and then you convert it to meters, and then you select this coordinate system as we did before, and then you can click on this eye to set this view up. Okay, so the next thing is, in order to draw the shape of the nozzle wall, we need to have a relationship. And what is that relationship again? So in order to draw this wall shape profile, as you know that the area varies with, so its pi r square varies with 0.1 plus x square. The other thing which we want to do is that we are going to have a axis metric as we did for the inlet pipe flow. We'll create only, we will only simulate a portion of this uh, nozzle. So we'll again use the axisymmetric assumption, and in that case we only solve this particular portion with this shape over here. Okay, so it will look like a 2D one. So for the creating of this 2D geometry, we need to first draw this profile. Okay, so so as you see, it's pi r square equals 0.1 plus x square. So as we move in the axial direction, this shape or r value, which will be the y or r value here, changes accordingly. Okay, so we need to draw this profile first, space claim. So in order to do that, we go here in the sketch menu, and then we click on this icon over here, which is the equation icon. Okay, so let's continue with that. So in equation icon, it starts with Archimedes spiral. You scroll down and you select at the bottom custom. So in the custom, so by default, the interval variable is t, but your variable is of course x. So take that x being equivalent to t. So start of this x, the range of this x is minus 0.5 to 0.5. So you just type that in first here. The interval is start is minus 0.5 and end is 0.5. So next thing is, what you want to do is that you want to type in the relation for y or r. Okay. So your y coordinate or r coordinate varies with x. So what is the relationship will be? So r, if you want to compute r from this relationship, what it will be? it will be 0.1 plus x square divided by this. In this pi goes on that side, divided by pi, and this is r square. So r will be square root of 0.1 plus x square divided by pi. Okay, so you just type that relationship over here. So I'm again insisting that t over here is your x basically. So by default in this space claim, it takes x as t. So I'm typing x square plus 0.1 divided by pi and then I'm taking square root. So make sure you have S capital for square root. Okay, so that will be the expression for drawing this profile. So when you will type enter, it will draw this profile over here. And then make sure that after completing this, you click on this green icon of check. Okay. So you just click on this green icon and then press escape, so that it comes out of this equation menu. Okay, so you will see it will have drawn this curve custom. You can name it as, for example, nozzle wall. Okay, so and then you can complete this remaining shape or geometry just by clicking on this line icon in sketch. If you have drawn into coordinate dimension, you just need to complete this profile. So 1 meter. That is our 2D sketch. So then you click on this mode, convert it into a surface, 2D surface. You just click on this 3D mode. It will convert this into a surface, if you see there. Okay, so that is our geometry for this case. In space claims, you just cross it and then open the mesh menu. So double click on mesh. It will import the geometry. Okay, so then what we want is we want to create a structured square mesh. So we have all square elements. So to do that, we need face meshing. So you just select this surface. See, that's face meshing. Then you need to specify the sizing. This surface, you just select this surface again. And element size is 0.025 meters. Behavior, it should be hard. And then you just generate the mesh. So that's it. That is the mesh we need, a coarser mesh in the start. And then you can specify the name the boundary conditions, boundaries. Left face is inlet, right face is outlet, upper edge is the wall. And this one is the symmetry axis. Then make sure that the boundaries are specified you wanted, and then you can move to the next step. So before moving to the next step, just update the mesh first. You know, so save the project as well. Click on mesh, update. Once that tick appears there in front of mesh, you can start with Fluent. So again, you need to go for check double precision, have parallel solution as well. Then you start Fluent. Okay, so because this is a compressible flow and supersonic one, normally for compressible flow, we go for density based solver. So you check that option, and because we are going for axis metric, so you need to select into the space the axis metric option as well. So density based and axis metric. Next, we need to specify our solution models. In compressible flows or in supersonic, we always turn on the energy because there is a variation in temperature as well. So we'll turn on the energy and we'll change the viscous model to laminar. Okay, then we go to the materials, fluids, air, and in air we go for, instead of constant density, we go for ideal gas option. So that is a norm for compressible, so where we have a change is in density as well. So because there is a change in density, we cannot go for constant density. We have to select ideal gas. Then we specify the boundary condition values. Okay, so in boundary conditions we have axis remains as axis, and at inlet we need to specify, so that inlet we are not given velocity over here in this case. So in this case we are given the pressure values, and in pressure values we are given two types of pressure. First one is total or stagnation pressure, and the second one is the static pressure. If you go back to the problem statement, it says that P node is 101325 Pascal, and the stagnation temperature is also given, and the static pressure at the exit is given. So there is a value of inlet pressure as well, which is not described here. The inlet static pressure is, if you can note down, it is 99348. It will also be typed there, I guess. So so here I'm specifying total pressure, which is 101325. and the static pressure is 9934. In total temperature, we click on thermal tab, and then in total condition, it is 300 Kelvin. Okay, the other thing which you need to do is, in contrast to the previous cases where we didn't change the operating conditions, and we said that the gauge operating condition is 101.325. So here, what we are doing is that in order to remove the confusion, what we do is that we type 0 over here as gauge, and we only deal not, so here in this case where we have fluctuations in density and we are given total pressures as well. So what we do is deal in terms of absolute or total pressures, not in terms of gauge pressure. So to remove any confusion, we just simply type 0 over here and tell the solver that we are dealing with absolute pressures over here. So make sure that
Excuse me,
जी
सर आपने इनलेट पर स्टैग्नेशन प्रेशर की वैल्यू ली है जो एटमॉस्फेरिक प्रेशर होता है, और सर आप कह रहे थे कि यहाँ पर स्टैटिक प्रेशर भी गिवन होना चाहिए। सर हम जब न्यूमेरिकल करते थे सर फ्लूइड डायनामिक्स में, सर हम तो स्टैग्नेशन प्रेशर को ही स्टैटिक प्रेशर मतलब ले लेते थे। सर आपने ये वैल्यू डिफरेंट कैसे ली है?
वहाँ तो हम पी नॉट स्पेसिफाई करते थे ना, पी नॉट, बट व्हाट इज द वैल्यू ऑफ पी? ओके, क्योंकि हमें वेलोसिटी नहीं पता, ठीक है, तो हमें पी नॉट और पी दोनों देने पड़ रहे हैं यहाँ क्योंकि वहाँ पे तो आप सिंपल टेबल्स वगैरह यूज कर लेते थे ना, तो यू हैव टू कैलकुलेट पी एंड पी नॉट, दोनों आपको देने पड़ेंगे। वहाँ तो आप सिंपली पी नॉट का रिलेशनशिप देख लेते थे, तो वहाँ यहाँ आप इसको आंसर्स में आपको दोनों देने पड़ते हैं। तो आप टेबल में जाके यू कैन फॉर स्पेसिफिक मैक नंबर और इफ यू नो अदर वैल्यूज, तो आप पी ओवर पी नॉट का रिलेशनशिप भी यूज कर सकते हैं। तो यहाँ पे आपको दोनों देने पड़ रहे हैं। तो वहाँ जब न्यूमेरिकल्स में हम देते थे, इट डजंट मीन कि वहाँ पी एग्जिस्ट नहीं करता या पी शुड बी सेम एज स्टैग्नेशन प्रेशर। वहाँ हम हमें सिर्फ स्टैग्नेशन प्रेशर रिक्वायर होता था एज इनपुट, यहाँ हमें स्टैग्नेशन प्रेशर और स्टैटिक प्रेशर दोनों स्पेसिफाई करने पड़ रहे हैं। ठीक है,
यस सर, ये बात समझ आ गई। सर आपने उसकी एक स्पेसिफिक वैल्यू यूज़ की है यहाँ पर, सर वो शायद गिवन नहीं है क्वेश्चन में। सर वो आपने कैसे लिया सर वैल्यू?
वही मैं मेंशन कर रहा था कि वो प्रॉब्लम स्टेटमेंट में गिवन नहीं है, लेकिन ये शुड हैव बीन प्रोवाइडेड, या अगर आपको पी नॉट और मैक नंबर पता हो तो फिर आप उससे भी निकाल सकते हैं टेबल से।
थैंक यू सर।
Okay, so in the outlet again, we are given another value of pressure. Just type that value over here. Okay, 3738.9. This is a static pressure value. And make sure that operating condition in all these cases are, we only deal with absolute values. So that is done. Okay, then you go for reference values and ask it to compute it from inlet. So again, I will remind that reference values are used, these are not used during the simulation or computation. These are used as in post-processing stage where you need to calculate various coefficients for CP, CD, CL, etc. Okay, so it doesn't, so if you are not interested in computing coefficients, then you can just skip this step. Okay, make sure them in the numerical scheme you're using second order up in numerical scheme. Okay, in monitors, you go to residuals. Again, we need to change this to 1 10 to the power minus 6. So here you will see that We have a fourth variable as well because we turned on the energy. So it also shows that residual level for energy as well. So then you go initialization, compute from inlet, and then compute from initialize. Then you go to run calculation, type any number of iterations, just typing 300 over here, and then you hit calculate. Okay, now you'll see that here it's also plotting energy mass imbalances or residual values also. So it's pretty fast. In just few seconds, it will touch. Okay, so then you go to post-processing stage. Again, I would say that you can also perform this post-processing in dedicated CFD post module as well, or you can perform this here inside the Fluent as well. Okay, so because we only took a portion of the cylindrical nozzle, circular profile, so we want to replicate that as a mirror and show the bottom part of the bottom side of the uh, nozzle geometry as well. So you just want to mirror the upper portion. So you just click. Let me go back to mirror that. You just click. So you click on results, graphics, graphics and animations, and then you click on views. Then go back again. Click on graphics, and then views here. This one. Views. Axis mirror. It says mirror planes. Okay. Mirror around the axis. Okay, so just click OK, and then you need to draw the various contours. So first you draw the contours of velocity, for example, vectors of velocity in terms of Mach number. So if you see here, it starts with a pretty low speed and then it accelerates to nozzle where Mach number becomes 1. And then because the pressure is low enough at the exit, it keep accelerating to supersonic speeds and it exits with a Mach number of almost 3 or 2 point something at the exit. So then you can draw various contours, like contours of pressures and velocities. Here's a plot of total pressure. So ideally, total pressure should be same whole domain. But because we have used a coarser mesh towards the exit, so as you refine the mesh and increase the accuracy of the solution, you will see that this disparity should grow. Then you can also display the contours of Mach number, etc. Okay, next, what we want to do is we want to draw our XY plot and compare our solution with the analytical result in the form of that data which I showed earlier. So that data was for Mach number. We are interested in.
एक्सक्यूज मी सर
जी
सर अगर इसमें शॉक वेव क्रिएट होती तो सर जो आप विजुअल रिप्रेजेंटेशन दिखा रहे थे वो किस तरह की डिफरेंट होनी थी, मतलब वो क्या उससे पता चल रहा होना था कि इसमें शॉक वेव है ये?
जी वहाँ पे एक तो कंट्रोल लेवल्स बिल्कुल चेंज हो रहे थे. यू शुड क्लियरली आपको एक रीजन नजर आना था जो कि नेक्स्ट अगर हम वेज वाले में करेंगे उसमें शॉक वेव आ रही है, तो आप देख सकते हैं.
ओके सर.
Okay, so what I've done here is I go back 10 seconds. Okay, next you are interested in plotting plotting Mach number. This is okay. So first you plot static pressure. You can see the behavior. So the blue black dots are at the values at the axis, the symmetry axis, and the red dots are the values for the wall, nozzle wall. So instead of these dots, you can also display them in line format. So you just click on these curves over here, back 10 seconds. So you're drawing pressure at the axis and nozzle fall, you need to select those. And then you can go to curves to change the shape of these curves. So click on pattern, it should be a line and there should be no symbols. Okay, so that is for the black one. Similarly, go to the next curve, it will be a red one, and then click on again. So you go to the curves again. So you need to change the pattern there for the red one as well. Should be no symbols. Apply. Okay. Then you can plot the Mach number variation. So Mach number, then you say plot. Okay. Now how to compare this with the analytical result? Remember, this is Fluent has solved a 2D case, but in our analysis, we while going to the theory, we solved it for a 1D case only. So should be some disparity, but not much. Okay, so in order to compare this Mach number variation with the analytical value, we need to upload the file which we had this mac underscore 1d.xy, which is the analytical result. So in the same menu of solution XY plot, just click on this load file. And then you browse to that file. So this is mac1d.xy. And then you load that, it will appear here, mac number. And then you just simply say that on axis and nozzle walls, plot. So it will add this data here in terms of green dots, which is the analytical value. Then you can change the shape or format of this. Convert it into a line to display a better representation. That's it for the converging diverging nozzle case. Okay, so the next problem, which is the a uniform supersonic stream is incident on a wedge. So the Mach number of the far field or the upstream velocity has a Mach number of upstream has a Mach number of 3. Then it hits a supersonic wedge with a half angle theta equals 15 degrees. You know that when it hits the wedge, it creates a oblique shock. So the upstream boundary conditions are Mach number of 3, static pressure is given at 1 atmosphere, and static temperature is given as 300 Kelvin. So then the shock wave will form here, a weak shock. We are interested to simulate that weak shock wave and visualize certain flow variables. You can also calculate shock angle, pressure coefficients along the wedge, and drag coefficients, etc. Okay, so you know that when it will hit, it will create a shock wave. And analytically, you can calculate various properties after the shock wave. For example, the first thing which you're interested in is this shock angle beta. You can calculate it as using theta beta m relationships. Then you are interested in the value of Mach number after the shock wave and values of pressures and temperatures after the shock wave. So let's supersonic wedge. So the normal proceedings, you go for selecting properties to 2D and starting in the space claim. You go to space claim options and you select units in terms of meters. You can also change size of the display grid. You scroll down, you can change the size as well. It's only for display purposes. Even if you don't want to change it, just leave it. Okay, then you want to select this first coordinate, XY plane. Okay, and then you need to just draw this far field and the upper half portion of the wedge. Click on sketch line, snap to the origin. Okay, this dimension, the vertical one is 1.3. Then this upper horizontal one is 1.5. This lower horizontal one is 0.5. This one, which I draw in the start. Okay, the next thing is that we want to, so it's a 15-degree wedge. So this angle will be 165. So you just keep moving it down until it says 165. Okay. So go back 10 seconds again. So you keep scrolling it down until it increases angle to 165. And then also you want to make sure that you are drawing it vertically. So there should be this right angle symbol visible as well. In that, only in that case, it will ensure that this point over here is at 90 degree to this. So keep scrolling it down to 165 and also make sure that you are drawing it vertically so that this right angle symbol is visible. So once that is done, then you will be drawing the right geometry shape. So then you just combine those two ends. So what we have done over here is, so this is that wedge with the 15-degree angle. Okay, this is the symmetry plane on the symmetry axis. So the other portion of the wedge is like that. So this half portion is here and the other half portion should be there. So we just want to simulate the upper half portion. So this boundary over here is the far field. Okay, we will be specifying the far field conditions. This is symmetry, and this portion over here is wedge. Okay, so geometry is completed. We just want to convert it into surface. So again, you just click on this 3D, then it will be converted to surface. Close it. And then we move on to the next stage, which is meshing. So I wrongly clicked on update. You don't want to do it, just double click on mesh. Undate that and remove this clear generating data. Just double click on mesh. Okay, so here's our geometry. So you can click on geometry and surfaces. So again, we are interested in structured meshing. Point 0.05. behavior is hard and generate. So this is a simple 2D mesh, structured mesh. Okay. As ever, the next thing is specifying and naming the boundaries. So upper three portions, these three sides, this one, and this one, all of them are far field. They will specify the far field conditions. And this portion is wedge. That portion is the symmetry. So that's it in the meshing stage. You just want to make sure that you have specified the correct boundaries, far field, wedge, and symmetry. Close it and then update the mesh. So once it's updated, you want to start the fluid. You can save the project as well. Okay, so click double precision. You can change the number of solvers to D, two solvers. And then you start the flow. Again, because this is a compressible flow with the variation in density, so you want to specify the density based solver. Okay, here I didn't click on axis symmetric because it's not a axis symmetric, it's not a circular geometry with differential third direction. It's a plane geometry, so you'll just keep it as planar. So energy, again, you need to turn that on for density based and change that to inviscid. Okay, in materials, air, I'm going to change that to ideal gas. The density doesn't remains constant, so leave that as it is. Close it down. Next, you want to specify the boundary values. So the most important one is the far field. Far field, it says that. So here you need to select the pressure far field because we're given a pressure value. So in contrast to the previous one, for the converging diverging nozzle, we selected the pressure inlet. So in pressure inlet, you specify that it gives you then an option to specify the absolute pressure and the static pressure. But here we are, it's not an internal flow case, it's an external flow case. So here we are specifying not pressure inlet, but a pressure far field. So once you select pressure far field, it only asks you to specify the static pressure. So it says that gauge pressure, but you can always convert that to absolute terms. So in the operating conditions, you can change the value to from 1013 to 5 to 0 again, and just specify that value over here. And then it asks you to specify the Mach number. So its Mach number is 3, and the flow direction is horizontal. Thermal remains same, is 300 Kelvin. Wedge is our wall, so it remains as wall. Symmetry is just a symmetry. You just need to select symmetry type. And operating conditions, as I said, just change that to 0. Okay, sometimes when you select the density based solver, sometimes you will observe, not in this case, but in more complex cases, you might observe that your solution is wiggling. So it's not converging, as you will monitor the residuals. So in that case, we will also discuss this condition, which is called CFL condition, which basically controls the stability of the scheme or stability of the solution. So here in solution controls, you have for density based solver, it's asks you to specify the quant number or the CFL value. So here's by default it's 5, but if you are experiencing wiggles or your solution displaying a problematic behavior, you just want to increase this number to a larger value, or you want to decrease it. So it's hit and trial. Normally you increase this number in order to get a more stable solution. So this is something which you want to keep in mind for the future simulations. Okay, then you can compute from far field. Residual level, you want to increase the accuracy to 1 to the 10 to the minus 6. Initialize resolution from far field. Specify the number of iterations and calculate. So again, it's very quick operation. In 77 iterations, it will converge, and then you can go on to the post-processing stage. Again, you can resort to post-processing inside Fluent or outside Fluent in CFD post. So first thing we want to see is the vectors of the Mach number. Mach number vectors display, you want to change the scale to 0.25 over here, this one. So you see that initially we had a Mach number of 3, which was coming from the far field. So it's incident on this wedge over here. There should be some wedge. So this is the wedge over here, and then we have a shock wave, oblique shock wave here. So across this oblique shock wave, as you see later in the contours plot, then across the oblique shock, we have a decrease in Mach number. So it then exits after the shock, the Mach number reduces to in the range of 2.20. Okay, we can see the contours of velocity clearly here in terms of Mach number. display. So here you will see that we had a mag 3 here, and then it's incident on. So due to this wedge, we have this shock wave being created. So across the shock wave, you can see clearly see the change in the color, which is specifying that from a higher Mach number, we are now moving on to the. So here we have a shock wave where we have abrupt change in the values, and then after the shock wave, we are seeing a more bluish here. So that means that there is a reduction in the Mach number value. So you see there is a rather coarse contour levels. You can increase the contour levels, and you can further accurately capture this shock wave if you further refine the mesh. So more refine the mesh in this region, the more accurate will be the position of accurate capturing of the shock wave. Then you can monitor other variable plots as well. Okay, so these are the analytical results after the shock wave. So M2 is 2.2, and we have seen that our M2 is also in this range, 2.2. P2 and T2, you can also observe those while drawing the pressure and temperature contours. Shock angle, you can sort of get an idea of shock angle. It's not a very accurate method, but it just gives you a sort of indication whether you are in the right range or not. How you can do that? So okay, so you can see that from here, from the wedge, starting of the wedge, here we have a certain line over here. Cross wave, we have this position where we have this location of the shock wave. So we are interested in this angle, which this shock wave is making with the horizontal axis, which is called beta over here. So in order to draw, in order to calculate this beta, we need, for example, a relationship like this. So it's called theta over here, but you can take it as a angle of the weak shock. So you can calculate this theta. It should be tangent inverse delta y over delta x. Okay, so delta y is the change in the vertical axis or y distance, and delta x is the change in the horizontal distance. So how you can get the change? So this is the x-axis values, and these are the y values. So you can, for example, draw a line here, draw any line anywhere in this, which is crossing this shock wave. For example, I am drawing a line. So I'm drawing a line at y equals. So I first draw a line, which you can do in CFD post. I'm not showing it here. So just draw a line in CFD post. Go to locations and create a line, then you can specify the coordinates. So the coordinates of these lines, this starting coordinate will be x equals 0, y equals 0.35, and this end will be x equals 1.5 and y equals 0.35. So it's not a fixed value, 0.35. You can just draw any contour any line as long as it crosses this oblique shock. So you just draw that line. So once that line crosses an oblique shock here, so then you want to calculate how you can calculate the slope of this one. That will be y2 minus y1 over x2 minus x1, or tangent inverse delta y over delta x. So how to locate what should be the value here? One indication is that as you move in the horizontal direction, you see a sudden jump in the values of, for example, Mach number, or sudden jump in the values of, for example, pressure or CP. So you just want to analyze the first, you want to just want to draw the plot of those quantities, for example, pressure or Mach number, and see the trend where it is going to shoot up or shoot down. So for example, on wedge, not this one, this is a CP plot on the wedge. Okay, so here I'm drawing this new line, which I just described. So it will be visible here, y equals 0.35. And then you can select this symmetry wedge and 0.35, and then you can draw the contours of, for example, pressure and pressure coefficient. You can also draw the variation of Mach number as well. So it will be something like this. Okay, so that thing is displayed here, pressure coefficient. So green dots are y equals 0.35, the line which we draw. So that is, you can see that at that particular line, the pressure coefficient is almost same, and when it encounters that shock, it suddenly goes up. Okay? So you want to observe the value of x where this thing starts shooting up. Okay, so the value of x here is just a guess, crude guess. Is, for example, you can take it as 0.97. Okay, so that was for y equals 0.35. Okay, if you observe symmetry and wedge, so that will form this. So in the start, you will have black dots for symmetry, and then you move in the x-axis. So this corresponds to wedge corresponds to, then you will encounter this wedge. So the wedge is here. So it's drawing this line symmetry, and then this wedge. Okay. So the green dots are for y equals 0.35 corresponding to this line. So it goes here, 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 and then you can see that CP or pressure, or there will be a change in the Mach number. So it goes up when it hits the Mach number. And similarly, these red ones are for this bottom line, here, 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 and then when the wedge starts, there will be a change in the values. So you just, so here there's 0.97, and this shooting up starts at something close to, for example, say 0.47. So that is delta x positions, and the upper one is the delta y positions. So it's a rough guess, so it's not very accurate, but it just gives you a hint of whether we are dealing in the right range. Similarly, you can also draw, so that was for CP. You can also draw a variation of Mach number and then observe how the Mach number is changing. So for example, again, for the same y equals 0.35 line, you'll see that the Mach number in this range remains almost the same. And then when it encounters a shock wave, across the shock wave, it suddenly dips to 2.2. So you want to observe what is the value of x when this dip starts. Okay, that dip starts, for example, here in this range, 0.97. We type that here, that is the y location is 0.35, and the 0 and 0.47 correspond to the y equals 0 position, this one over here, and will be this wedge encounter. Then that it starts, and that corresponds to almost 0.5 or something. Okay, so you plug those values in, and then you calculate the shock angle beta. So an analytical solution says that the shock angle is 32.221. You should get the similar values, not close accurately there, not at 32, but maybe just some plus minus 3 to 32. Maybe you will get 30, 35, depends upon how do you capture this. Okay, so if you want to increase the accuracy of this solution, because we started with a very coarse mesh, you can of course double the size of the mesh and then get a more accurate solution. The other idea to refine the mesh is only by refining the region where we have a shock wave, and that's what we call the mesh adaptation, and that depends upon certain indicators. You might wanna look online for this mesh adaptation, how to perform that. If I find some good tutorial, I will also demonstrate how we can sort of refine the mesh only in the regions where we desire it. Because refining the mesh all around, we are not interested in the region here, in the far field. If I just double the mesh, I'll just increase my computational cost, and that will be the waste of time and computing resources. We're not interested here, we're only interested in this region over here. So rather than refining all around, we just, what if we, so it will be a better strategy to just refine in the locations where we, which are more important for our solution point of view. So that is called mesh adaptation, and maybe we will discuss that later as well. So these two tutorials are for today. Next week we will go for some more tutorials, and also I will hand over some more assignments to you. Okay, any questions?
No, sir.
I hope all of you have submitted the first assignment. I haven't checked the numbers yet, but everyone has submitted. Okay, that's it for today then. Thank you.